Okay, welcome everyone. We're going to get started in a few seconds. Thanks, Will, for this light entertainment while we wait for people to come in. Okay, great. Let's get started. Welcome everyone to Ethproof call 6B. This is the first time that we're repeating a topic, specifically proximity gaps, because we have just so much content to discuss. And if you'd like to join the Telegram group, here's the QR code, or you could just join in with the URL ethproofs_community. There's some good discussion there. Zooming out, I'd like to say a mission accomplished on one of the biggest missions of 2025, which was real-time proving, trying to prove every single block with low latency on a reasonable cluster, drawing in particular less than 10 kilowatts. We had 3 different teams at Ethproofs Day that showcased this, and we have more teams over the next few weeks and months that will also achieve it. So fantastic congratulations to everyone involved. In 2026, what I expect will happen is that there's going to be a shift away from performance. We still want to keep performance, of course, but we want to do things above and beyond just raw performance. So looking at, for example, the foundations of security, trying to avoid these proximity gaps conjectures, trying to make sure that our proof sizes are reasonably small, and making sure that we can deal with prover killers and liveness and uptime and all of these good things. So this has been the schedule of 2025. We're wrapping up with call 6B. And as you can see, there's already more of a focus as we approach the end of the year towards 2025. And in 2026, the 3 calls that we tentatively have scheduled are on security as well. And the next call will be on guest diversity. So not only do we want a diversity of zkEVMs, but we also want a diversity of guest programs that get compiled to these zkEVMs. And we already have today integrated 4 different guest programs, which is really amazing, including some more recent ones like EVM1 and LEVM from Ethrex, zkSync OS, in addition, of course, to our EVM. So here's a little update to the zkEVM tracker. In yellow, we have some of the new updates. So we have 2 new columns, the 10 kilowatt proving, which 3 different teams have achieved. So congrats Airbender, SP1 Hypercube, and ZisK. And we also have a new column around the usage of proximity gaps, and whether that's proven proximity gaps or conjectured. And we're already seeing a kind of industry shift towards provable proximity gaps, with SP1 Hypercube and ZisK leading the way, but others like OpenVM kind of signaling that they will be moving to provable proximity gaps. And we also have 2 new integrations on Ethproofs from Powder and LambdaClass. Now here, just a super small update, I guess, is RISC-0 is no longer integrated with Ethproofs because Fara, as one of the provers proving them, has stopped proving, but I'm expecting them to go back in this top category very soon in 2026. They're working on a V3, which is much faster. And we also have 2 new zkEVMs for which the name has dropped. So we have the LambdaVM from LambdaClass, and we have the zkDTVM from AntChain. I think that stands for Deterministic Virtual Machine. And then finally, I've added kind of a new category at the bottom here, which is zkEVMs for which, from my perspective, development has paused, at least temporarily. So these are zkEVMs that might not be actively maintained, but of course, they could jump back up if they come back to life. Okay, so talking about security foundations, we want to move to proven gaps. And just yesterday, we had George post a new, or maybe it was today actually, yesterday, Ethereum Foundation blog post on that, and George will be talking about that shortly. And final slide. This is today's agenda. So we're going to have a few updates, starting with Jordi, who will talk about how they kind of very, very quickly moved to 128-bit of provable security, which is great. And then we're going to have miscellaneous updates from various zkEVM. So for example, exciting news, Linea is going to be building a type 1 zkEVM, trying to join the race toward mainnet grade zkEVMs. And we also have other exciting announcements coming up. And we will have 8 presentations, so extremely packed schedule today. We might go slightly over the 2 hours, but really the highlight here is all of the papers, 6 different papers that have come out very recently, in addition to all the papers that we talked about last time. And one of the big themes here is that the proximity gaps conjecture is taking punch after punch after punch. Every time it receives a punch, the researchers will tweak the conjecture and form a new conjecture. And now we've had 3 rounds of this where the conjectures have been proven false. But we're going to end with some hope, a result from Venkat, which actually shows that the proximity gaps conjecture is true in some other settings, like the randomized setting. And we're giving Venkat an honorary 20 minutes to show his result, partly because of what it is fundamentally, but also partly because Guru Swami is basically from the celebrated Guru Swami Sudan decoder. Okay, so without further ado, I'd like to invite Jordi to the stage to talk about 128 bits of provable security for ZisK.
Hello. Well, I'm very proud to announce that we are currently releasing version 0.15.0. I think that we are running the last continuous integration right now. So if everything goes well, it should be in a few hours available. And this version, mainly what it does is, it's already 128 bits provable security. The interesting part is that the proof size still be below 300K. Currently, it's about 240K without compression, but actually compression does not do anything. So this is the final proof. And all these keeping very much keeping exactly the same timings and the same performance that we had. This is possible mainly for many things. Mainly there is an important optimization in the Keccak circuit. It's a fully new arithmetization and some cool ideas that we divided by just 1 order of magnitude the cost of the Keccak arithmetization. But there was also a lot of re-engineering in the circuit, in the aggregation circuit. Mainly there were some optimizations there, like reducing the top of the trees, just only proving it once. We added grinding in there, and we added some little bit more polynomials there, so we keep the order. So there was a lot of engineering there. Okay, and in this version also there is some MODEX fixes optimizations to keep that Fusaka and all these more or less keep working. And of course, we are still open source and quantum resistant. So this is very much the update for this version.
Congrats. Quick question. Is this using Goldilocks with a degree 2 or 3 extension?
Goldilocks over degree 3. We didn't change that.
Okay, perfect. And super cool that you've managed to keep the proof size under 300 kilobytes at 240. That's super cool.
For this, we in the final step, actually, we just do a binary tree. So this is much shorter, and with that we keep all more or less the same size.
Okay, interesting. I don't know about the details of that, but I'll ask you offline. I'm quite curious. Next up, we have Alex from the Linea team. Alex, the floor is
Yeah,
yours.
so thanks for having me. On our side, the team recently shipped Fusaka on the mainnet of Linea. So that was a very important upgrade for us because we in the span of June to December we covered London to Fusaka. That was really important for us to test whether it was actually achievable to keep up to date with Ethereum while doing the arithmetization by hand, and we think it's a success. Other things that are coming up is the completion of the migration to Collabor. So it has taken a considerable amount of time because it meant rewriting a lot of the prover. But once complete, we already have some benchmark, and it is going to be a super massive performance boost. We are using Quartic extension now, but are going to reach it very fast to sextic in order to be fully at 128 bits of security. One very interesting thing in how we are approaching type 1 compatibility, because being type 2 by hand is kind of proved to be possible, but being type 1 is more complicated because you have to be good at doing RLP encoding and K-track encoding, and those are super hard to do by hand. So what we developed is a language named zkEVM, which is partially fleshed out, but already put in production for some of the use cases. We use it already to prove Black 2. So it is at that level. So it supports control flow, it supports recursion, it supports wide degree because it's Collabor, so 32-bit times 6. And then there is all the losses in the protocol. And so the language compiles into heirs, and from that we will implement Patricia Merkle trees and RLP encoding. So one feature we will need will be the support for memory addressing, which is not currently implemented but will be very soon and is being actively implemented. And those are the main things that are missing to be type 1 anyway. So we think we are very close.
Congrats. And great to see that you're so flexible while being super low level and performant. One quick question from Ulrich. Why degree 6 extension for 128 bits of security, presumably as opposed to maybe degree 5?
Yes, so the reason we do it is, so degree 5 is possible if we use grinding, but we don't use grinding. Like some of the loss we have come from the proximity gap, but also from the enormous size of the traces. Like if we simplify a little bit the soundness loss in a protocol that use Fara or any code-based thing, there is a loss that is associated to the least decoding error, because we tend to use Fry as a polynomial commitment, but formally that's not true. There is a soundness loss associated with that. A few dozens of bits, and there is a usual Schwarzschild loss, which is kind of proportional to the trace size, so 30 to 40 bits. So this cumulated means that you need at least 6. 5 is not going to give enough security out of the box.
Got it. Ben in the chat is pointing to the new result by Ulrich. Maybe degree 5 is possible. But yeah, thank you so much, Alex. Next up, we have Diego from LambdaClass.
Thanks a lot, Justin. We are pleased to announce that we started building the LambdaVM. And the idea behind this is the same as we had in Ethrex, and what we did related to execution clients. So the idea is to make this VM like really simple, minimalistic, track a lot the number of dependencies, keep them at a minimum. The idea is that we are not only going to develop the VM, but also the proof system. Everything is going to be directly incorporated into it. We wanted to make it post-quantum secure from day one and achieve the 128 bits of security. We are going to build a RISC-V 64 virtual machine. And we are working closely with our partners to make these very comprehensive spec, have everything like clearly written down and make it really easy then to audit and formally verify. So it's part of the same philosophy. We think that this can add a lot of value. We of course like a lot many of the VMs that they've made, and they've made like great contributions, but we want to make something simpler and also to add diversity to the VM space. So that's the news. We are like trying to move as fast as possible so as to have like the minimal version, and I hope we can show some things really soon.
Okay, great. Looking forward to the code base being open sourced, and great to see more zkVMs looking to have a super simple code base. It's reminiscent of Jolt and LeanVM, which is great. Thank you, Diego. Next up, we have another new zkVM, ZP1 from Vishal. Vishal, are you here?
Yeah. I cannot share.
Oh, strange. Okay, let's move on to the next speaker and we'll sort you out. Next up, we have Ming from Ceno, who will talk about real-time proving.
Yeah, hello. Thanks, Justin. So I'm looking for how to share screen.
That's it. We can see your screen.
Okay, cool. Okay, so yeah, I'm Ming from Ceno team. So today I will share some progress update for the Q4 for the milestone. So right now the project overall is in the late alpha and early beta stage. So and in the Q4 we are majorly achieved, like the first one is the precompile acceleration. So previously we don't have much precompile, so we integrate a few precompile for acceleration, and we also have the multi-shot support right now to prove the mainnet block. Yeah, and the November we are integrate the GPU end to end, and right now the base layer is in the RISC-V GKR, and the recursion is in the SNARG, which is powered by the OpenVM. Yeah, and here we show two simple diagram. It's a simple breakdown for the data we have so far. So right now we divide the execution in we divide the proving flow into 3 stages: the emulator and the RISC-V and the RISC-V GKR and the recursion part. So in the November we are optimized it, and so far with on the December part we have some result now. And right now we are still trying to optimize, because we optimize more on the shard number. We are reduced from the 30 to 16. So then the emulator part is occupy more proportion right now, and also the recursion part is also occupy more proportion if we optimize the GKR part like more and more. So later we will try to also working on the more general optimization for all the part. This is by the way, this data is proving the block which is around like 20 million gas in a single 4090 GPU. Yeah, and the right diagram is like, right now we also have another challenge is like in all the shot our GPU prover is not very like the performance is not very consistent across all shot. You can see some shot we can reach a very high like cycle, but some are below, like some above below average. So for now and beyond, we are working on like firstly we try to reduce the shot to be less than 10. This is our first goal. And with that, we can probably make all shot reach the 4 megahertz, and later we will try to make all shot reach the 10 megahertz. Yeah, and once we achieve that, then we will move on to the cluster real-time proving. And right now we already on the Ethproof stage, so we are also on board to reach Ethproof live sooner. And that's it. If you are interested in the GKR security or like some integration with the GKR some check or or interest in the Ceno flow, we feel free to feedback and discuss. That's it.
Perfect. Thank you so much. We have a question from Kev. What CPU was used here in the benchmarks?
CPU, right? Is it
Yeah,
CPU?
which CPU was used?
Oh, CPU, I remember it's like EPYC, which is like 64 core for now, but I forget the real number is based on AMD. Yeah. But the CPU in here, the majorly work of CPU is the witness generation and the emulator part. And for all the other part, like the RISC-V GKR layer or the recursion part, we are switching on the GPU mode.
Nice. Kunxian has shared in the chat that it's an EPYC 9554 64 core. Great. Looking forward to see you on Ethproofs production. And I know your backend is quite different from the others, so it would be great to see the performance deltas there. Thank you so much, Ming.
Yeah.
Vishal, do you want to try sharing your screen again?
Yeah. Oh, still not.
Still not. Okay. Maybe it's like a setting on your computer and you need to kind of restart Zoom. I'm not sure. Next up, we have Gal, who is joining as a new proximity prize judge. So I wanted to give him another opportunity to introduce himself.
Thanks, Justin. Hi, everyone. Justin thought I should introduce myself. It's a good idea. So I have just joined the prize committee. So unfortunately, I have the difficulty of trying to parse everything while things are still changing every day. So just a bit about myself. About 6 months ago, I guess, I finished my PhD at the Weizmann Institute with Moni No and Elon Yogev. Now I'm a postdoc at Bocconi University in Italy. Most of my work has been on IOPs, more the theory side, but in this field, theory and practice are very close to each other. So that somehow turned into practical things like stir and whir. More recently, I've looked at security of Fiat Shamir and things like the minimal size of group-based SNARGs. So that's me. Thanks, Justin.
Perfect. Welcome to the panel of judges, and we've updated the website proximityprize.org. I'm hopeful that very soon, maybe early 2026, we'll have the actual formal rules of the prize, and we can start delivering some of the prizes. Cool. Vishal, do you want to try one last time?
Yeah. Still not.
Okay. I mean, do you want to just give an intro without
Yeah.
slides, I guess?
Yeah. So it's a Zippel at ZP1, an open source RISC-V work in progress zkEVM. So we are using RB32 IM with the Circle stack on Mercent 31. It's totally open source. It's been 10 days we open source, and it's dual license, and it's currently in research and pre-alpha phase. So what's the motivation of doing this? It's challenging, and I see it can have a huge impact. So what's Zippel Lab and who we are? We are a small independent research and development team, not backed by anyone currently. And what next? What's the roadmap? So in Q1, what we will try to do is release white paper and work on recursion and GPU acceleration, then try to prove EVM minute blocks in less than 12 seconds. And then in Q3, early Q3, we will try to work on security formal verification. And in early Q4, we will try to real-time proving on Ethproof. Thank you.
Amazing. And if I understand correctly, this is, at least historically, been mostly a one-person effort, and it's especially impressive because you're still at university, just finishing your final exams. So looking forward to the future of ZP1. Cool. So that finishes off the section on quick updates. Now we're going to have slightly longer presentations, ranging from 6 minutes to 20 minutes. First off, we have Will and Fara with a 6-minute update on Ethproofs.
Thanks, Justin. Yeah, so if you didn't have a chance to join Ethproofs Day in Argentina, it was a blast. Thanks to everyone that participated. There's a YouTube playlist that's available now, so all the talks are online if you want to go check them out. I used my talk to speak about the overall magnitude of this entire effort that we're all a part of, and likened it to a public-private partnership, where on one side you've got the dynamism of these private industry participants, the zkEVMs and the provers, breaking new ground and setting new benchmarks day in and day out, and really just blowing our minds. And then on the other side, on the public side, you have all of the EF teams and researchers that are really kind of setting all of these non-negotiables in this direction, and really trying to make sure that all of those industry actions are sort of done in concert and in alignment with broader Ethereum protocol objectives. And so in between is where Ethproofs sit. So as a literal interface, the website itself, and then as this kind of community mimetic wrapper trying to help drive alignment along all of these objectives that the researchers are positioning. And so as Justin mentioned earlier, 2025 was decidedly the year of performance. And with a lot of the blog posts that you're seeing posted recently and conversations with researchers, it's clear that 2026, the center of gravity is moving more towards security, diversity, and resilience, all with performance in the backdrop as table stakes never going away. So this week we also launched a blog, and there's a couple blog posts up if you want to go check them out. The first one is all on these 2025 highlights, a lot of links to great content. And then the second part is all about 2026 roadmap objectives as we see it now. Obviously, this is constantly being updated. And so one thing that we know is for certain is that Ethproofs itself as a platform, we really want to try to scale up and improve the back end and the operational functionality of the interface. And so really working to make sure that we reflect the operational profiles now that we've seen 9 months of activity on the site, and all in service of providing clear, consistent, neutral performance benchmarks. So there's a second blog post that's also on the website that's all around, in sort of the spirit of that, that's about prover personas and GPU price indices. And I'll throw it to Fara to talk about that one.
Yeah, so when Ethproofs launched, the only game in town was for provers to submit proofs for every 100 blocks using a single GPU prover. Then beginning with ZK Cloud in March, and more recently in the push-up to Ethproofs Day, we saw the emergence of multi-GPU provers submitting proofs for every block. So in 2026, we will begin to roll these out as what we are calling prover personas on Ethproofs. So when creating a new cluster, teams will need to choose which goal they are targeting. Additionally, back when we launched, we started with a snapshot of cloud-hosted GPU configurations for several vendors. This approach helped us bootstrap our efforts, but it needs to be modernized to be less brittle, more scalable, and reflect the reality that most provers are converging on a limited set of hardware. So in response, we are introducing a simple GPU cost index, an average of globally available pricing for a single readily available 5090, which can then be multiplied by the number of GPUs the prover is using. We feel this approach provides lots of advantages and reflects our mission. The mission of Ethproofs is to measure tons of proofs over a long period of time to help surface directional trends, not to be a detailed cost model that is easy to game and nearly impossible to verify. Some of these advantages include bucketed data, meaning provers submitting proofs for every block won't distort the data for those submitting every 100 blocks. It also opens up new design spaces. We can easily provide a simple admin dashboard for team onboarding and cluster maintenance, and we can derive a reliability or liveness score that punishes teams for missing proofs. From there, we can take the most performant provers and add them to a real-time proving cohort. And once we have that foundation, we can begin to monitor teams even closer. Anytime more than one fails to prove a proof in under 10 seconds, we can designate that block as a prover stunner. And anytime more than one queues a block but fails to submit the proof, we can designate that block as a prover paralyzer. So monitoring all of this behavior can help us generate a resilience score and surface issues. Because if 2025 was the race to prove Ethereum in real time, 2026 is the race to mainnet grade zkEVMs.
And the race continues. So we're excited to announce the next Ethproofs Day, which is going to be just prior to ETH CC in Cannes on Saturday, March 28th. And then we're calling that day Beast Mode. And then the following day is going to be a chance to learn more about the post-quantum cryptography and post-quantum consensus fast finality efforts that are also underway. And we're calling that day Fort Mode, which is on Sunday. So we hope to see you there. We'll drop links to both Lumas here in a second, and feel free to sign up. Thanks.
Okay, amazing. Right on time. Any questions from the audience? So one question from Reza is the 6000 the RTX Pro 6000? Yes, that's what it is. It has bigger, more VRAM. And yeah, thank you so much, Will, for all the coordination, and Fara for being, this interface. I think this is a great mental model, and going forward, we want to be, have a finger on the pulse, both on the community side of things, but also internally to the EF. And we have at least 4 different teams within the EF, essentially dedicated to zkEVMs, and the closer we can work together, the better. Great. So I don't see any questions, so we can move on to George, who will talk about soundcalc, as well as his latest blog post.
Hello, everyone. Let's do the classics. Can you see my screen?
Yep.
Got it.
Okay, fantastic. Okay, so yeah, let's go a bit into this blog post and this push towards security and foundations that Justin and Will have been talking about. But before we do that, let's do a little bit more of like world building. And like if you've been following these calls, you know that projects relying on conjectures, proximity gap conjectures, on heuristics. Lately, they've been working on pretty shaky ground, and days pass and conjectures crumble and bits of security fall with it. So us as like the EF cryptography team, I think we feel quite uncomfortable relying on such conjectures that one day they hold and the other day they don't. So from now on, we want to focus on provable security only. And not only that, but I think there is something to be said about bits of security as well, where many projects, they, for performance reasons and for other reasons, they are going with like 100-bit security, which is reasonable in some ways, but also you need to go and count bits and see how many hashes Bitcoin does, and do some margins, and this is not the way we want to think when we're talking about L1 mainnet grade security. So we want what we're trying to do is sort of set the goals to provable security and 128 bits, which I think is a reasonable goal that the rest of the industry does. So that's sort of setting the stage. And over the past months, we've been creating, from talking to teams and trying to understand how they calculate soundness and how they calculate security. We found that each team does it differently. And one thing we did is create soundcalc, which is basically a universal soundness calculator for hash-based proof systems. And what you do is you have your zkEVM, you go to soundcalc, you integrate your proof system, you integrate your PCS, you integrate the parameters of your circuits, the trace length, if you're doing fry, what rate, what folding factor, all this stuff. And then soundcalc essentially spits out an overview, which is quite detailed because we're dealing with many circuits and recursion and stuff. But in the end of the day, it's basically the final proof size, like the final proof, the wrapper proof, how big it is, and also the final bits of security throughout all the circuits. So, here you see, it's 53 bits of security in the Johnson bound regime, and the circuit with that security, like the offending circuit, the weakest link is the RISC-V circuit, for example. Anyhow, so with this tooling, having this tooling and these foundations, let's go a bit into the blog post. So what we're trying to do in this blog post is set up some milestone for 2026 that basically we want in the end of the year to take us to the ideal security level. So let's go to the milestones one by one. So by the end of February, we expect projects to have integrated to soundcalc. What does this mean? It means that, if you're using some sort of a univariate to multilinear adapter, we would like you to integrate this component into soundcalc. If you're using a lookup for input-output consistency, or for memory checking, or if you're using multiset hashing, we want you to also integrate those components into soundcalc, and then also integrate your circuits into soundcalc. You're not alone on this. We are very actively working on soundcalc, so please reach out and we will help you integrate your stuff. But we do want your assistance. We cannot do it on our own. So that's the first milestone. Then by the end of May, which is before the Glamsterdam hard fork, we want projects to have ended up with 100 bits provable security and less than 600 kilobyte proofs, which I think we think is an achievable goal. And then by the end of the year, we want projects to have 128-bit provable security, so the industry standard, and proofs less than 300 kilobytes. These numbers are not random. The proofs need to be small enough because they will be eventually transmitted through the networking P2P backbone of Ethereum. And also, these numbers are not random in the sense that we talked to the teams and we got positive reactions and teams being optimistic that these milestones can be hit. Right. And because you have the slide in front of you, and you can see these items, there is also one item related to recursion that I would like to go into. Basically, again, from talking to all these teams, one thing that has been sort of quite different between all these teams. They're all using hash-based PCSs, they're all doing pretty much reasonable stuff, but everyone is relying on recursion to sort of take the big EVM trace and chunk it up and do continuations and do all the nice stuff that allows such a big trace to end up with a very small proof. But because each team is doing this recursion differently. Like they're using different techniques. They're sort of using different fan outs. They're using some projects are using circuits. Other projects are using a RISC-V machine to do the recursion. Like we see lots of differences in the recursion. So one thing that we want as part of the milestones is to put a bit more sanity into this process. So like we basically want to end up with recursion specs. We want projects to document how these components connect with each other, the techniques, the lookup arguments, the glue basically. Like we want the glue to be documented so that we understand what we're dealing with, and we ideally we would want to integrate the glue as well into soundcalc. So these are the recursion related milestones, and eventually we do want also to prove soundness, like an informal soundness proof that this whole recursive thing produces the security that we want. Like treating the proofs as black boxes. Why does this recursive thing produces the security that we want? Anyway, we will go more into these formal details as time moves on. So these are the milestones from the blog post, and I just want to take a brief second to talk to why we think these are the right milestones for this point in time. Basically, we think that we spent last year obsessing about performance, and rightly so, because we want to de-risk the entire project in terms of performance, which is like the main component. But at the same time, we think that this is the right time to pin down the security part, because if we keep the security as a free variable, basically, like we will never ossify the foundations, like the proof system, the PCSs. So we hope that by the end of this year, the foundations of the zkEVM have ossified, or at least stabilized in some way, and this will allow us to do more proper audits. It will allow us to do more proper implementation level specs. It will allow the formal verification initiative to do more deep work. So yeah, we think this is the right time to basically set up this foundation. And wrapping up, I know that the blog post is quite high level, and my talk here has been high level. So we are writing down more specific details, particularly about how we think recursion specs should look like. And we plan to publish a more formal technical document on the milestones early next year, like in January. And also we're working on revamping Ethproofs to make it more security focused, so that we basically highlight teams that improve their security the way we would like them to. So yeah, that's it basically. Now you know what the blog post is about, and let me know if you have questions. Thank you.
Thank you, George. Feel free to unmute or raise your hands or ask questions in the chat. Question from Reza: how to adjust for extra bits of security when comparing zkEVM proof generation times? If it matters, let's say we're proving 60 million gas blocks.
I'm not sure exactly. Reza, can you say a few more details on what you mean? Maybe Justin, I don't know if you got that.
I mean, my best interpretation here is that if you have longer traces, that affects security a little bit. And so as you increase the gas limit, maybe there's a degradation of security. But my hot take here would be that these are very minimal, but I don't know. Ben is saying his interpretation is that if different provers have different security levels, how do you compare proving times? I guess what we're trying to do is to normalize the security levels so that they do become more comparable. And I guess the other observation is that at first approximation, when you increase security, you don't really degrade prover time. You increase the proof size, which will affect prover time indirectly because of recursion. But at first approximation, it's a fairly minimal degradation in proving time. Cool. I think that's mostly what we have in terms of questions. Thank you again, George. So now we're going to start the hardcore mathematics part of the call, starting with Alistair, who had an initial paper a few weeks ago proving that the conjecture was incorrect. And then right after that, we have Giacomo, who will talk about a paper that builds on this initial result and makes it even stronger and made the attack more potent. Alistair, the floor is yours.
Hi. Let me see if sharing works.
Yep.
Oh. See that, but I can't maximize it now. No, it's this side.
It's pretty big, yeah.
Okay. So yeah, so we have this paper on Reed Solomon's proximity gap conjectures, Elizabeth and I. We had two results, one of which overlapped with the paper 4 days before that Ben and Angus presented, and one of which overlaps with the paper 2 days later that also got presented. Okay. So the basic idea was this conjecture in the deep flow paper about list decoding up to capacity was already known to be incorrect from about the 1950s. So Peter Elias looked at this, and there's basically a threshold below which some codes are list decodable. I'll give you the number for this later, and above which every code has exponential size list. Of course, when I say some codes are list decodable, we still have no idea about Reed Solomon, and there's still a huge gap. Yeah, and the point of this paper was to see if this also applied to proximity gaps, and the answer to that is pretty much yes. So just like Ben and Angus's paper, we looked at the chance that a random word was close to the code, and from that you can get a proximity gap for correlated agreement failure. This is the formula that we got for the bounds on this probability of being close to the code. And yeah, here's the formula for this Curie entropy that appeared in the list decoding bound statement. What does that mean? Basically, very soon after this list decoding capacity bound, we end up with proximity gaps completely failing. For anything far from the code, we can find something which you could just take at random. And almost every point on the line, apart from the endpoint you started from, is actually close to the code. And to go that, you only have to go as far as this form would suggest. This term in the square root is the square root of almost the whole gap in between proximity and this list decoding bound. So it's this lower bound is very much closer to the list decoding thing than capacity.
Ben is asking, what is wrong with n minus f minus 1?
Okay, maybe I'm being paranoid here, right? So there's one thing where everything that's not in the code, right? So if something's not in the code, it's n minus f minus 1.
So covering radius is n minus f. Unless I think you have the same convention as us. F is message length, not degree or something, right? So covering, you can find a deep hole.
No, F is the number of errors.
Distance.
Yeah.
Yes, right. So you can find a deep hole of distance n minus f, and then most of the line will be less. So I think you're off by 1.
Maybe we're off by 2.
By 1, I think.
Moved by 1 in
your K must be less than capacity.
Yes.
So covering radius is n minus f for you. Your K must be less than that. But
so it must be less
not,
than n minus f minus 1. That makes sense. Okay, yeah. That's one out. The end thing is that we think the list decoding capacity theorem is probably tight for correlated agreement as well. And this holds, I think, in a bigger regime, more useful regime in practice than Ben and Angus's thing. So that's where we got with that. Again, how big is this? It's about 1 over log Q. It's the gap from capacity. And we can do a more complicated formula here that goes off the edge, the binary entropy. And the technique, we used agreement sets. We're talking about disagreement sets, but it's equivalent. And we're being inexact in that we don't require to guess exactly what the we can agree on some things where we weren't assuming we agreed. If you do this, then everything ends up much nicer. All the numbers end up being simpler. Everything ends up being uniformly distributed, and everything works. Right. So concretely, it's like we have 2 sets of size f, and you interpolate polynomials outside of them. If the 2 things intersect by the intersection of these things is smaller than the minimum distance, then clearly if these things are low degree and we get a code word, then it must be the same code word for these 2 things. And otherwise, the events that these things are code words are independent, and almost everything, all our events are pairwise independent, and the variance ends up being small, and then everything ends up working pretty nicely. The variance of the number of sets where this works end up being small, and everything ends up nicely. And then we made some conjectures, which the original conjecture from 3 weeks ago was proved wrong by Fenzi and Sanso. Now the updated conjecture from the ePrint we published today was survived until yesterday. So yeah. So our suggestion was we take the existing conjecture, with this eta that was the distance to capacity, and instead make it the distance to the list decoding capacity bound with this entropy term. Now the question's a bit is Curie entropy. So originally we were suggesting Curie entropy for the field size. And then we thought, okay, let's be conservative and move it to the characteristic, which gets the wrong thing for binary fields for sure. And then that doesn't work either. And now maybe the minimum of the characteristic and the domain size n is going to work here. This is a conjecture that I don't know of any things wrong with it, but we can almost certainly do better for small characteristics. So for binary fields, we really don't have a clue. So that's the conjectures. We had some other results. We got the list decoding implies correlated agreement result that was also an overlapping result with Cofferty, Haböck, and many other authors' paper. But that result has like this failure probability for correlated agreement of about 1 over k, where k is the like the degree, degree plus 1. And that's not ideal. I mean, it's still a useful result, though you might have to repeat the test a few times. If you batch enough stuff, it still works. And then we looked at this regime where the domain is in a subset, in a subfield. That's why we were suggesting the characteristic instead of the size of the field for extension fields. And basically what happens is that correlated agreement fails when list decoding fails, just like in Fenzi and Sanso. And this is not the 1 over k. This is the complete failure we were getting before, where every point on the line, but the one endpoint that's far from the code is close. And again, yeah, this is why we were suggesting HP, because we get when you go past the list decoding capacity for the small field, basically you can use these small field words which are close to small field code words, and lots of them, to build the correlated agreement failure. So that's our results. So one thing I wanted to highlight that I don't think anyone really has done any work for, we're doing lots of work on this conjectures, but it's not obvious just because the conjecture fails that the SNARGs are actually insecure. Rather, what happens is, so, I can easily find something that's far from the code, which if I proved it was close to the code will allow me to forge a SNARG proving basically anything. We have this quotient which I can easily commit to a word that looks like this rational function, but it's far from a polynomial. But if I combine it with something at random, then I end up with something which is close to a polynomial with high probability. The only problem is I've got no idea how to find it. Like, what is this polynomial that's close to? If I find the polynomial that's close to, I can probably prove it with Fry. I can go through with the entire Fry proof for this thing being low degree. But I've got no idea how to find it, and we don't have any algorithms that work beyond the Johnson bound, right? Even if we knew this was, there was something close, we have no algorithms to do it. A list decoding might be completely unfeasible beyond this list decoding capacity bound. That was, the classical result. The list size becomes exponential, but we just need one element. The only trouble is that this problem, bounded distance decoding for Reed-Solomon codes, there are actually hardness results for it, but none of them really apply for this random word case. There's a couple of people showing it's NP hard, and one paper that has this more general reduction from discrete logs for extension fields. None of them work, and this last one is not post-quantum, and really. Decoding random words seems a really hard problem because everything looks random and you've got no idea which way to go. Yeah, that's all I wanted to say in the 10 minutes. I have lots of slides on techniques if people ask questions.
Thank you, Alistair. So is it fair to say that you've kind of ended your presentation giving us a little bit of hope that actually these conjectures might come back from the dead in terms of proofs of it being hard to find attacks. So is it fair to say
so
that
there might be a computational hardness result here,
right?
A hardness assumption that makes everything work, right? This is the thing you'd hope if you can prove this hardness and you can get a reduction. Of course, getting that to work, getting that to be post-quantum, which was part of what we wanted from these SNARGs in the first place, adds to the difficulty. But yeah, there is a hope that these things are secure, but we have to make a new assumption other than just the random oracle model that we're doing for these Merkle trees.
Got it. But maybe these assumptions could also be proven at some point.
Well, it's cryptographic assumptions. No, they can't be proven.
Okay, got it. Giacomo, you have your hand up.
Yes, I had a question. Like when you're talking about the conjecture, the new conjecture is in a part you replace the query entropy with the entropy of the characteristic of the field. And I was wondering because the attack that we did in particular, I'm not able to bring down exactly to the characteristic of the field. For example, if I have a Reed-Solomon code defined over a binary field, I need to still choose my evaluation point to be over like some larger subfield. So I will not go down to, size 2, but like maybe 2 to the 16, say if my size is 2 to the 15, for example.
Yeah, absolutely. We don't know what the right answer is for really small fields. So for things like this 32-bit field, the characteristic is tight. It's going to be tight. But if you have this subfield, which is, smaller than the logarithm of the extension field size, then there just aren't enough. If we list decode something which has the domain is the same size as the field, there just aren't enough code words for the list size to be huge.
No, but what I'm asking is slightly different. Like, so your attack, the new one for this field. So suppose, for example, I choose a Reed-Solomon code over 31-bit field, but I choose my evaluation domain points to be over the extension. So they're like over extension, say a SID-stick extension. So my code is still like over I still have like an extension, but my evaluation domain is now over the extension and I'm not over the base field. Like does
right. Yeah. Then you might be fine. So in particular, but you end up having to do something interesting to get points in the base field. So if you look at like say what Circle FFT does, then yes, I'd imagine that's looking at the extension field list decoding capacity bound and not the subfield. But not only do they evaluate on the extension field, but they're also like effectively some kind of folded Reed-Solomon code where you have the conjugate and the point itself in your evaluation domain, but you give them as the same point. If you look at it as a code over the original field, then you're giving the real and imaginary part, but you don't imagine like your Hamming distance should not be less if the real part is wrong and the imaginary part is the same. It should be smaller, and as a result, the effective alphabet size is the extension field size and not the base field size.
Wait, Giacomo, are you saying you can dodge your attack if you choose your domain to not live in the base field? Then
that's right, and the reason is because effectively your alphabet size is bigger. I mean, bear in mind that folded Reed-Solomon codes are secure to capacity, right? We know now, and I'm sure there's going to be a talk on that.
Yeah, so we can if you basically the only case in which my attack, and I'm guessing Alistair's one as well applies, is when if you encode like base ID elements, if you only do base multiplication, our attacks applies. If instead you have to do base extension or extension base, then as far as I know, both our attack would not apply in that case. But, like intuitively.
Giacomo, do you want to take it from here?
Sure, I can share my screen. There we are. Okay, can you see this? Oh, sorry, the Zoom thing always goes in the wrong places.
Yeah, we can see it.
Okay, good. Then I'll go ahead with this. I think it's a very nice segue. So this I'm going to talk about small field hash-based SNARGs, or let's sound the conjecture. So this is a work with Antonio Sanso, and it's going to contain a few things like the attack itself. There is more of an observation and an actual attack. It's just combining two results previously known in the literature. But I want to talk a bit about some of the other works that we've done, the things that it will connect to some write-up which will eventually come out regarding the proximity prize. So I think this could be like also a quick tidbit on what me, Dan, and Gal have been working on. So let me start talking about this, and I want to introduce first a toy problem. Toy problem is a very loaded term in this. There's been the very famous ETH Stark toy problem like a long time ago. And now you might be asking, okay, look, Giacomo, why are we introducing a toy problem? So I don't think I'm a particularly, smart individual. Like I cannot hold many things in my head. So being able to having like a very minimal example which allows me to get intuition on the security of a protocol, I think is a very worthwhile thing, and it allows us to think. So this toy problem is basically taken from the security analysis of war. It's a very simple protocol, and if I can prove this, I'm confident I can prove larger protocols. And analyzing the soundness upper bound and lower bound of this protocol will further inform our understanding of what we really know about these problems. And it's a very simple protocol, and it fits on one slide. So basically, you're going to be trying to think about constraint codes. So these are codes. So you have F1 and F2, which are, in the honest case, they're code words, and they must satisfy some sort of linear constraint of them. So this dot product with V. V and U1 are inputs were given by the person who's running the protocol. So what's the protocol? Well, the proven verifier, the verifier just asks for a random linear combination. The prover sends the random linear combination, and then the verifier spot checks that the encoding of the linear combination agrees with the random combination of the two input code words. Very simple and nice. In this you do the queries, and you can do a soundness analysis of this protocol, and you can show that the soundness error, and in fact a stronger version of round knowledge soundness error of this protocol, can hold given and is bound by three quantities. One of them is the mutual correlated agreement error of the code. This is what proximity gaps have been traditionally about. One term which depends on the list size of the code. And one term is 1 minus delta to the t, which is essentially the proximity error. And so these are the three errors. And why you should say that these are errors that are calculated by a parameter delta, which is basically how many errors we can tolerate. And these errors, they have counteracting behaviors when delta grows to 1. For example, the MCA error, as delta goes to 1, will go to 1. The list size error, it will actually go to something even larger than 1 once delta goes to 1, because it will cover the entire space. And instead, the 1 minus delta t will go to 0 as delta goes to 1. So finding a security analysis which gives you what you want, the efficiency parameter you want, is about really finding the right balance between minimizing t, which of course, like the larger delta is, the smaller t can be, and maintaining the other two errors under control. So this is the toy protocol, and is what we're going to be starting with. So we can prove soundness for as long as I give you an expression of MCA and the list size, I can actually compute the soundness. For example, if I set t to be 128 and I use a Rich-Solomon code of a typical size, using provable bounds, I can show this as approximately 64 bits of security. So this is one part. Now, for this presentation, I'm going to just talk about the list size part. So I'm not going to talk anything proximity gaps in this part, because I also believe the list size, is a more fundamental notion as part of the work in CS25 and in BCH-KES 25, as shown, that the list size ends up being like a fundamental hurdle that we have to overcome in order to actually be able to give stronger security guarantees of this protocol. So what is this notion of list size? Well, I'm giving you a word, and this word could be a code word, it most likely will not be. And I want to look at the Hamming ball around it and see what things are close to it. So within these unique decoding radius, there will be at most one, but in general, there might be many more. And the intuition of why you should care is that when you have when in an analysis you have to deal with a list size, you usually have to do a union bound. And this union bound is problematic for the soundness error. And this appears in a lot of places, like for example, in the constraint folder within the toy protocol, in auto-domain samples. It's very inherent in anything you do hash-based. And in fact, you can even vary some of the protocols that we know about to get security which does not depend on proximity gaps, but only on list decoding conjectures. Further, we think that proving this is at least as hard as proving distance preservation is at least as hard as proving the list size is bounded when we're talking in the Johnson to capacity regime. Even more fundamentally, maybe you could say, look, Giacomo, you have this toy protocol, you have an analysis which relies on MCA and list decoding, but it might be just a feature of the analysis that you're doing. So part of the reason why we want to have a toy problem to analyze is that we want to show that there are some lower bounds on the soundness that this protocol guarantee, which depend on quantities of the code that we know how to analyze. And this is how you show that exactly that the problem that you care about is inherently related to the security of the toy problem. And what we show is that this toy protocol has a soundness error of this form. This might be like a very annoying expression, but you can look at the first term to be roughly the list size of the code divided by the size of the field, which is the same term we showed in the knowledge soundness analysis. The attack for this is exceedingly simple. What you do is you start by choosing some f with which achieves the maximal list size radius, and by definition this must exist. Then you start. We start the claim by choosing a v and a u which satisfy two properties. So first of all, you want to start with an invalid claim. So in particular, you want that for every code word close to f, the claim that you start with is invalid. And second, you want that this v is chosen so that actually the you don't have many collisions when you apply this linear transformation to words in the list. And turns out that you can do like a very easy averaging argument to show that there must exist a V which achieves exactly the expression in the bound. Then the attack is just that when V chooses the randomness for the combination, you find some word which is close to the input code word, which satisfies the constraint that you care about. And turns out that this succeeds with probability S over F. So what does this show? That basically any lower bound on the on list size directly translates to an attack on the Troy problem. And our goal is now to find like the best result, or we find the best lower bound that we find on list size and the distance delta star at which we maximize the success probability. Some caveats. So this is a very theoretical attack. You don't actually, it is not concretely instantiatable. We don't know how to actually run it in practice. You rely on some of these problems that Alistair was mentioning that are thought to be hard. And also it's a very generic attack. Any code that we use will actually fall short of attack. I am using no structure with Solomon codes at all. Any code, well, any linear code will also satisfy this attack. So this has been a bit of it. And this part here of the computational efficiency seems to be common in a lot of other works which exploit proximity gaps. Okay, now we have a framework, and our last result of the paper is just an instantiation. We combine two results. So first is this classical averaging argument by Peter Elias that shows that the list size of the code must have this must be a list of this size, which depends on the size of an Hamming ball. This bound already leads to an attack, and an attack with success probability is kind of maximized when this error is like 1 minus rho minus log of f. And we notice that we actually can do better. In fact, by like, this is just that slide, I swear. In a lot of cases in practice, you actually have the fact that the code that you use is an extension code. So it's a code that is obtained by taking a code over a base field and then embedding it into an extension field. And in this case, we show that that you can actually get a success probability which is maximized when the delta depends on the size of the base field rather than the extension field. Concretely, these chooses for like common parameters around a 9% degradation in the security margin, and we have tables for like a bunch of settings that we analyzed. So this is what we did. But I think the main contribution is like having a nice toy problem that you can analyze. You can give upper bound and lower bound. It enables you to like make informed decision on what your protocol is about. Thank you.
Thank you, Giacomo. I guess one question that I have is, do you think this toy problem could be used as the basis for the proximity prize? And I guess we could rename it to the prize problem. Mm-hmm. And then we can look at the best of an attack and the provable security, and then kind of pay per bit, if you will, of uncertainty that is cleared off.
So I think so. There are positives. I think me, Dan, and Gal, we're working very hard to find a nice formulation that for the prize, which captures a lot of the liveness and soundness properties that we care about. I think this can be part of it. I believe that this is something that could be a good starting point for a lot of the prize discussion. I also am a bit worried, because there might be a result to come out which don't have a direct impact on the price problem, let's say, but are nonetheless breakthroughs which, in my opinion, like for example, if somebody showed at some point that with Solomon are at least decodable up to capacity for fields which are maybe slightly larger than the koala bears that we care about, and then somebody later improves that bound slightly by actually applying to the price problem, then I think there is like there will be a situation in which we cannot base the price solely on this toy problem. So I think it could be like, I think it's definitely something that people should try to improve and see whether they can tighten the margin, and it will definitely tell which progress we're doing, but it might be that a more nuanced and a more qualitative rather than quantitative decision might have to be made. So this is I don't want to commit myself. I think it's part of the solution, but not all of the solution.
Justin, I think the toy problem is a great motivation for the problems in the prize, for the challenges in the prize. So it's kind of serves more as a explanation for the community for why the prize is so important.
Got it. Makes sense. And I guess now that I have both of you, Dan and Giacomo, when do you feel you think we'll have prize rules ready?
Okay, maybe I'm a little worried to commit, but we're hoping for sometime in January.
Okay, wow, that's sooner than I expected. Amazing.
Oh, then February. If you're expecting, yeah.
Any other questions? Feel free to just unmute or raise your hand. If not, we're kind of tight on time, so that's great. We can move to the next speaker. Thank you so much, Giacomo. We can move to Ulrich, who will be presenting a constructive result, which is great to have as well.
So, hi. Thanks for the invitation, first of all. Can you hear me loud and clear?
Yep, all good.
Okay. Share does work?
Everything works.
Okay, so I'm gonna talk on a note how to generalize the Guruswamy-Sudan list decoder analysis from Ben Sussen and others from the 2020 paper to prove mutual correlated agreement. So this is a note that I pushed online a couple of weeks ago. I shared it in the course of the last year with several people, and I expect also some of them are here in the call. So, okay, let's just 10 minutes. I want to keep it simple. Let's start. Correlated agreement, or what is a correlated agreement theorem? So given two words over a domain D with values in a finite field F, so what is the theorem, or what we want to have is if with notable probability, with small probability, a random linear combination, so the probability with respect to Z is close to the code, then also U1, the interleaved code word, U0, U1 is close to the interleaved code. In other words, they're together close to the code. There exists a joint agreement set, which is sufficiently large, over which both U0 and U1 correspond to code words. Okay, I will work, and it's quite useful, not just for mutual correlated agreement, also for correlated agreement, to work with the proxy. And the proxy here behind correlated agreement, equivalently strong, is the following collinearity claim or property. So if with notable probability the random linear combination is close to the code, then a fraction of them, of the proximate polynomials, are collinear. They lie on a line in the code. Okay, so that
we have a question from the chat from Michele. For which choices of Z?
I just say for notable probability. So if sufficiently many, so let's say if for sufficiently many Z's from the field, the random linear combination is close, then a certain fraction. I'm not going here to specify. It's a big O fraction here. So a O of one fraction. Anyways, I don't think so. So then a certain fraction of approximates lie on the line. This is the theorem. So once you have proven this is like the bare metal notion behind correlated agreement. So all the correlated agreement theorems I know, also the mutual correlated agreement theorems, go essentially that road. So they show that a fraction of the proximate code words of the proximate polynomials are collinear, and from that you are as good as finished. So this is what I call the proxy property. So I will focus more in this talk on collinearity of proximate instead of talking about correlated agreement. I hope, I'm not sure if this answers the questions. I hope it does. Okay, and now mutual correlated agreement. this is a notion that goes back to the Word paper and also Seilberger, who used the notion, I think, strong correlated agreement in her work. So given U0 and again 2 words, so what's the difference here is a type of so you say except for few Z, there might be some few bad apples, but except these, if you throw them back, all the proximate, all the proximates for whenever they exist. So when I talk about except for few Z, so let's consider the good Z's where I have proximate, where linear combinations are proximate, except for few Z's, the proximates of the linear combination stem from proximates of the interleaved code word. So that's the statement here. So nothing. So first of all, one direction. One observation is obvious. If you have correlated agreements, so if you take something that's close to that word in the interleaved sense, then of course a random linear combination is also agrees on the same set, so it's also close. So one direction is easy. The other one is just you claim more. So every proximate except for few bad apples, every proximate stems from proximates of the interleaved word. And in terms of more geometric picture here is just except for few Z, you can partition, take all the proximates you have for all the C's where there are close enough polynomials. Take all and they can be partitioned into collinear ones. So that in one set, big picture is, so in other words, there exists a collection of lines such that except for these few bad proximates, all the others lie on one line, one of these few lines. So this is roughly the picture one could have in mind here. This is why I prefer often to say it's a global or list correlated agreement theorem. Okay, so results, just an overview for general linear codes. It's not here, maybe I'm missing something here. I hope I'm mentioning everybody. Yeah, results here, correlated agreement versus mutual correlated agreement, which mutual correlated agreement is a much modern notion, came up much later. So yeah, in a unique decoding regime up to mean distance of the code over 3. This was essentially Garo paper together with Roth and Seymour. This was then strengthened. I mentioned also to forget one of the early work of Swastik Kopati. And then these were generalized to double Johnson bound, 1 minus 4th root of essentially row of the code, let's call it that way, and 1.5 Johnson in the Deep Fry paper. So this is like the classical correlated agreement. Can you see my mouse cursor, by the way? I'm not sure.
Yeah, we can.
Okay, so that's the classical correlated agreement. And for general linear codes, the mutual correlated agreement was proven double Johnson bound. It was in one of the early version of Seilberger's work. I think it's the Katam paper. And even before that, or almost around the same time, the Chinese team, I forgot the name, which had their more global proof of correlated agreement up to 1.5 Johnson. So both of them can be somehow viewed as a generalization of this track of work. Okay, and then for Reed-Solomon codes, you can do a bit better. Use algebraic decoder analysis, and yeah, the classical BCIKS paper, the proximity gaps paper, proves it for both up to mean distance over 2 and the Johnson bound. That correlated agreement theorem holds. This was recently just a bit improved by the new ProxCaps paper of Swastik, Dan, and I, and afterwards, yeah, in terms of mutual correlated agreement, the paper that explicitly defines it under that name also proves it for delta for mean distance over 2 in the UDR. And actually, I hope I still have a few minutes left. This talk is here about how to prove it for Reed-Solomon codes between mean distance over 2 up to Johnson. How many minutes left?
Less than 2.
Okay. So then let's skip over how set intersection games work. Okay. So Ritz-Solomon codes. Okay. So they use error correcting decoders, algebraic error correcting decoders. In the UDR, it's a Bellekamp-Welch. In the LDR, the list decoding regime, it's a Goswami-Sudan decoder. And the main idea, what they do is you consider, because you want to understand how the random linear combinations, can they be glued together for all these different Z in some sense? So they consider the word here where the Z is not yet taken, it's a symbolic variable. So they consider this word as a word in the field of rational functions over Z in the variable Z. And the goal is to infer something about the decoder in that large function field here, field of rational functions, given that we know for certain specific Z's, the decoder succeeds on that specialization of the word. So that's the main idea. And for the Goswami-Sudan, it looks like this. If you never saw a Sudan decoder, you probably won't understand it. So you start off setting up and interpolating bivariate polynomials. I hide here the Z because it's over the large field. I'm not sure if it's still displayable. So the Z's are here, but just a bit more hidden. So you start you set up this interpolating bivariate polynomial for that given word over the large field, and you may always think of it factorized into irreducibles. So these are the irreducibles. There's some content here which doesn't depend on Y. And the thing is, now let's look at it. For certain good Z's, we know that the decoder succeeds. That means for this good Z's, where we have approximate polynomial PZ, we know that that this PZ must belong to one of these irreducibles, must be the solution of one of them in Y. And the goal is, so again, for each good Z, the proximate belongs to one of the irreducibles. And the goal is to show that that one of the irreducible has a smooth solution, has smooth dependencies on the Z. So it glues together the different Z proximates for Z. And now, almost last slide. So what's sufficient, and that's really where all the tough works of the BCIKS paper goes into. What's sufficient is if the irreducible factor of the Goswami-Sudan bivariate, if it hosts more than this number of proximates, I already took the new bound from the new paper, then I really can say that, just jumping back here, that then we can include approximates together. And that's good enough for correlated agreement. Essentially, you show, yeah, okay, that's good enough. And the funny thing is, once you know this, and this is how the proof is written in the BCIKS paper, once you know this, the only thing that leaves is the pigeonhole principle. So because the sufficient consistency talks about one RI. If one covers sufficiently many proximates, then it's already it defines the line, it defines the correlated agreement proximate. And now, given that we have more of these irreducible factors, the only thing, if you have L irreducible factors, by the way, L is the number of factors here, or let's say the Y degree of the Goswami-Sudan interpolant, then yeah, just use the pigeonhole principle, blow up that number by number N, then you know if you have more than these, then at least one of them must have the initial must exceed the initial threshold. That's what a proof does. And for mutual correlated,
3 minutes over. Sorry to interrupt.
Okay. So
we're very
this is really the last slide. here. There's nothing to say. There's just one change. Just look at the pigeonhole principle a different way, and that's it.
Okay, got it. Thank you so much, Ulrich. And I just want to give a heads up, actually, a shout out, sorry, to the attendees. We have roughly 100 attendees who have made it 1 hour and a half through. So congrats to everyone who stayed so far. Thank you again, Ulrich. Next up, we have Mrinal, who will be making another 10-minute presentation. Mrinal, the floor's yours.
Share my screen. Give me a second. I think Ulrich has to stop sharing. For
I'm trying to find out how that works. I think didn't I stop sharing?
There you go. I did it for you,
Ulrich.
Yes. Thanks.
So I believe it's another constructive paper, which is nice.
Thanks, Justin. So I'm going to talk about a joint work with I'm going to talk about a joint work with Prahlad Harsha and Shoham Chatterjee at TIFR. And this is going to be a deterministic list decoding algorithm for Reed-Solomon codes. Okay, so this is a very different audience than the typical audience that I've given technical talks in. So please stop me, ask questions with this. I just want to convey the statement, and that's all. So the setting is the following. We are over a finite field F. We are going to look at Reed-Solomon codes. The dimension of the code will be k plus 1. So we are going to look at degree k polynomials, univariates. And the set of evaluation points that we are going to work with is some subset of size n of the field F. So this is a set S. The rate of the code is k plus 1 over n. The minimum distance is 1 minus k over n. And combinatorially, the distance of the code already tells us that this code can be uniquely decoded from error half times n minus k over n, and can be list decoded from error n minus square root nk by the Johnson bound. In terms of algorithmic statements, we have had unique decoders, efficient unique decoders for this code since the 1960s. So these decoders are deterministic algorithms, and they run in time polynomial in n and log of the field size and require that the agreement is greater than n plus k over 2. There are various versions of this starting from the 60s. In the list decoding regime, so here we are trying to decode from agreement square root nk, so match the Johnson bound. And here we have algorithms of Sudan and Guruswamy Sudan from the 90s. And their running times depend on whether we are looking at the deterministic version of these algorithms or the randomized version.
Now, we might be looking at the wrong slide. We're back to the first slide. At least that's what we can see.
All right. Let me just try again. Can you see my screen?
It's taking a while to load. Maybe if you try turning off your camera. I'm not sure if it's an internet issue.
Yes, I can do that. Sure. Does that help?
Okay, yes, better.
All right, sorry. So can I just continue? Is that okay?
Yeah, go ahead, yes.
All right. So so I was talking about list decoding algorithms. So in terms of efficient algorithms, we know how to do this from algorithms of Sudan and Guruswamy Sudan. These algorithms require the agreement to be greater than square root nk, which is the Johnson bound, which matches the Johnson bound for the code. And the running time of the algorithms is, these algorithms run in time polynomial in n and log of the field size if we are happy with randomized algorithms. And if we want them to be deterministic, then they run in time polynomial in n and the field size. The main question that we look at in our work is to understand if we can list decode Reed-Solomon codes up to the Johnson bound, so match the performance of the Guruswamy-Sudhan algorithm. But we would like to do it deterministically, and we would like to still run in time polynomial in n and log of the field size. I stumbled across this question a few years ago, and I wondered why this hasn't been studied in the coding theory literature before. And there are good reasons why that has been the case. So in typical coding theory settings, the field size for Reed-Solomon codes, the field size is typically polynomial in n or even n. In which case, poly in n and log f is just poly in n and the size of f. So there's nothing to be done. The other setting where something similar holds is if we are working over finite fields of small characteristic. Over such fields, we know how to list decode deterministically in time polynomial in n and log of the field size. So this question of having a deterministic list decoding algorithm for Reed-Solomon codes is interesting only when the field size is much larger than n, or the characteristic is much larger than n. So from a coding theoretic perspective, especially with respect to applications, I think it's of limited interest. But from a computational algebra perspective, I think it's still a very basic technical question to understand. The source of randomness, the use of randomness in these list decoding algorithms of Sudhan and Guruswamy-Sudhan are to efficiently factor bivariate polynomials over the underlying field. And these bivariate factoring algorithms in turn rely on univariate polynomial factorization over the underlying field. And for univariate factorization, we know how to efficiently factor univariate polynomials with randomness in time polynomial in the field size in log of the field size and the degree of the polynomial. But we don't know deterministic algorithms for this problem, even for very special and simple cases like factoring polynomials of the form x square minus a. All right, so our result is a polynomial in n and log of the field size time deterministic algorithm that list decodes Reed-Solomon codes up to the Johnson bound over all finite fields f. So this matches the performance of the Guruswamy-Sudhan algorithm, but is deterministic. And our main sort of technical observation in this is built around the fact that the polynomial factorization instances that show up in these algorithms can be solved efficiently. They are special. And they are special in two ways. The first way they are special is that we are trying to factor polynomials for which we have access to a lot of their zeros. And the other additional structure is that we are looking for very special factors of Q in these list decoding algorithms. As far as I understand, this does not seem to provide any general insights towards the complexity of univariate polynomial factorization over finite fields. I would be happy to be wrong about that, but to the best of my understanding right now, that's the case. So what we have really are two different algorithms based on what kind of agreement we are looking for. So if we are trying to decode with agreements greater than square root of root 2kn, this is what Sudhan's original paper worked with. Here we have a slightly simpler and cleaner algorithm that's based on Newton iteration. And if you want to decode all the way up to the Johnson bound, which was the setting in Guruswamy-Sudhan, then we have a slightly more technical algorithm that's based on this idea of Hensel lifting that's very widely used in the polynomial factorization literature. Let me just flash the main technical theorem and I'll stop. I believe I have a minute. So the main technical theorem is the following. So suppose we have a bivariate polynomial q of xy and a point alpha beta. And for this discussion, let's assume that q is monic in y. So now let's classify the irreducible factors of q into three sets, A, B, and C. The the set A consists of irreducible factors P of xy such that when we substitute x by alpha, so we get P of alpha y. This is a power of y minus beta. The set B consists of irreducible factors P of Q such that P of alpha y is not divisible by y minus beta. And the set C consists of everything else. And let Q sub A, Q sub B, Q sub C be the product of polynomials in the sets A, B, C, respectively. Then our main technical theorem gives a deterministic algorithm that takes Q as input and alpha beta as input. And it outputs QA, QB, QC in time, which is polynomial in degree and log of the field size, and deterministically. And so this is sort of the main technical engine combined together with some more ideas. This is what gives the final deterministic algorithm. I'll stop here. Any questions?
Thank you, Mrinal. I guess I'm trying to connect things with proximity gaps. So I guess proximity gaps is related to list decoding, and you've made an advancement in list decoding up to the Johnson bound. I guess a couple questions. Like, one, does your work provide insights potentially beyond the Johnson bound? And two, are you also interested in working directly on proximity gaps? Is there a problem that you're looking into?
Yes to the second question. As far as I understand, no to the first question at the moment. So beyond the Johnson bound, I'm not sure that this provides any insight at the moment.
Okay, but are you optimistic that some insights could be found, and is that something that you're also looking into?
Yes, I think so. I actually didn't expect that we'll be able to prove this without being able to say something about deterministic factorization, but this turned out to be an easier problem than what at least I had imagined earlier. So maybe there are things to understand. Yes.
Okay, perfect. Thank you so much again, Mrinal. And I see we have Dmitry who's ready, who will be showing a very recent result from just a few days ago. So the floor is yours, Dmitry.
So hi everyone. I do mathematics, so my talk is going to be mathematical without much mentioning the applications or the meaning of this. But hopefully I can convey sort of the basic idea of what we found. We found this maybe 2 days ago, so this is very recent. So let me describe the setup again. So we have the proximity gap conjecture, which is stated and restated again and again in different forms, and we're trying to sort of understand to which extent it holds. So in essence, the proximity gap says that for general codes, but we will specifically focus on Rich-Solomon codes, that you have this code, which is a subset of some linear space over FQ. And the claim is that if you have a line, then to check that the whole line is close to the code, for this, it is enough to check that sufficiently many points of this line are close to the code. So the general philosophy is that you have Rich-Solomon code with some parameters and taking some line L. Once you know that some fraction of its points is delta n close to the code, then you know that the whole line is close to the code. Okay. So getting closer to the parameters, the original conjecture was that you can actually take the fraction of the points to be polynomial in n divided by q. So q is the total number of points on a line. And the claim is that it suffices to check that polynomially many in n points are delta n close to the code. Okay. So n here is the size of the domain on which you evaluate your polynomials of degree at most k. Okay. So what is delta? So depending on the sort of distance to the code, the whole picture has different flavor. So you have this unique decodable parameter 1 minus rho over 2, below which everything is understood pretty well, and we know that it's actually enough to have linear in n number of points. So epsilon, which is linear in n divided by q, is already sufficient. Okay, then you have the next parameter gap, which is up to Johnson's bound, which is delta smaller than 1 over square root of rho. And there it is known that the conjecture is true, so it is enough to have the epsilon, which is polynomial n over q. And the sort of conjecture is that this is also true up to the capacity regime, so all the way up to 1 minus rho. So beyond 1 minus rho, nothing is happening because all points are 1 minus rho times n close to the code. Okay, so we want to bridge the gap and understand either the failure of this conjecture or to prove rigorously this conjecture is in this regime. Okay, so basically the result we found is that there are constructions where this conjecture fails when you get close to the capacity. Specifically, if you take delta, which is eta close to the capacity regime and eta is much smaller than 1, then the epsilon that you must take should be at least exponential in 1 over eta divided by q. So in particular, if you take eta, which is, say, 1 over log squared n, then you already get something super exponential in n. So the conjecture that it's polynomial in n doesn't hold. Okay. So you kind of need to incorporate the exponential dependence on 1 over eta. Okay, so maybe at the end I will mention what I think should be true or how to state the conjecture. But for now, let's briefly look at the construction. It's very easy and very explicit. So we work with a prime field, so a field with prime number of elements. And then we evaluate the code at the nth root of unity, where n is a power of 2. This is, as I understand, what is actually done in practice. And n is power of 2 divided by p minus 1. What we do is we split this subgroup of the multiplicative group into S cosets, where S is again a power of 2, which divides n. So the size of each coset is going to be m, n over s, n is equal s times m. Okay. So now our parameter rho is going to be r minus 2 divided by s. So this is the degree of a polynomial we allow divided by the size of the domain. And the line that we are going to consider, so the space fp to the n can be thought of as functions from the domain to fp, right? And we look at the line which is passing through the point given by a function x to the rm. So this is above the allowed degree. So the allowed degree is r minus 2 times m. And we are taking a polynomial which is of larger degree, so it's not in the code. Okay. And the direction of the line is again given by a next monomial, which is x to the r minus 1 times m. Again, this is not in the code. Okay. And lambda varies over fp. Okay. And the idea is, which was also present in the previous papers, that you can take some subset of your domain, evaluate the smallest polynomial which vanishes on this subset of the domain, and then you will get a polynomial which has these two terms, the two large terms, and all other terms are going to be of degree at most k, which will allow you to see that, you know, this specific point for some specific lambda is going to coincide with some polynomial of degree k, at most k, on some large part of the domain. So the computation is actually easy. You just take r different cosets, you evaluate the polynomial which vanishes on the union of these r cosets, and it's not hard to see that you have cancellation when you multiply over a given coset, and you have these gaps. So the polynomial is actually a polynomial of x to the m. It has a leading coefficient 1. The next coefficient is some sum of roots of unity, and the rest is going to be in your in the code, because it's going to have degree at most r minus 2 times m, which is exactly the parameter rho. Okay. So then the only question that you need to be concerned with is to check that when you sum psi1 plus etc. plus psi r, then you actually get many different values in your field. So this is one thing to carefully check. In different regimes, it has different flavor. But if you take a field which is large enough, so roughly speaking, you know that R is like constant time S, and so you choose R tuples out of S possible roots of unity, and essentially you should think that if your field is exponentially large in S, then you're going to get almost all of these sums are going to be different. So you're going to have exponentially in S many sums. Okay. So basically the parameters that you get is your eta is 2 over S. So this you can see, you know, the parameter rho is R minus 2 over S, whereas you have R over S for the domain, right? For the distance, because you have R cosets where you coincide. Okay, so the distance between 1 minus rho and delta is in fact small. It is 2 over S, but the epsilon must be actually 2 to the S over P. So roughly, it should be exponential in S. Okay, so you can take some specific parameters to break the conjecture with polynomial. If you take like eta, which is 1 over log squared n, then you can take any field which has size which is at least exponential in eta, in 1 over eta, sorry, and then epsilon is going to be super polynomial in n over p. You can also try to take a smaller field and aim at proving that not, you know, all the sums xi1 plus xi are distinct, but that you actually cover almost all of the field. So probably with smaller field, you can come up with examples where epsilon is very, very close to 1, but we haven't done this yet. Okay, so I guess that one way to look at this is that in the original conjecture, I think the safe way to phrase the conjecture is that you just fix delta ahead of time, and then your bound, which is polynomial in n over q, so this bound should be this constant which depend on eta. And presumably the actual dependence should be exponential 1 over eta, but this is like a more precise statement. But what I want to stress is that it's still quite unclear what happens between the Johnson bound and capacity regime. What we know is when you get close to the capacity, then everything fails spectacularly, but maybe below that, there is still some hope for this to be true. Okay, I finish here.
Perfect. Thank you so much. And yeah, I was going to ask how you think you can fix the conjecture, and you already shared that. I guess it's great to see that, you know, mathematicians that are seemingly completely disconnected from the blockchain world learned about this. I'm curious, how did you learn about this conjecture and the desire to solve it?
I think I saw like on Facebook someone like wrote about
Facebook.
The proximity. I mean, I do have some friends who are like more into like blockchain world and stuff. Yeah, I doubt that this conjecture is sort of known in the math community. I think not really.
Just to verify, is it only for prime fields, or does it work for? Does this apply also to extension fields?
I think it should also apply to extension field. I mean, the only thing is that you need q minus 1 to be divisible by n, and the only thing construction uses is that you have a cyclic group in the multiplicative group of the field.
In the article, they made an attack about field f to the m. They thought it's very exciting to do this with prime fields. So.
Oh, right. Yes. Yeah. I think our original thinking was that it has been done kind of for like a fields of characteristic 2, and so we tried to do in the opposite side for prime fields, but it works for like extension fields as well.
And is the paper public somewhere?
No, we initially wrote it like 2 days ago, so we haven't actually like written up it.
Dan, it's in the Telegram group that you're in.
Oh, perfect. Okay, thanks.
By the way, if anyone's actively working on these proximity gaps, we have a Telegram group of about 40 people. You're more than welcome to join if you're actively researching. Great, thank you so much, Dmitry.
So can I make a quick comment? So your proposed fix, it seems like you wanted to fix in advance how close the proximity parameter can reach 1 minus rho, and then let this constant O of 1 depend on that choice, right? So I think this is essentially what we did. I think this might be broken by Giacomo and Antonio's result. In other words, what they showed is that you can break this by essentially letting the extension degree get large. So you kind of fix your word that has a large list size, something like that. And then you let Q grow. You keep the characteristic the same and let the extension degree grow. And this list size sort of won't change. And that seems to break that conjecture. So I'm not sure that approach works. Thanks to Giacomo.
I had the feeling that their parameters tend to 1, that like both rho tends to 1 and also delta tend to 1, but I'm not sure. I should check again. But
we can discuss. Yeah. I'm hoping to get a gathering of people to discuss the fixed conjecture and what it should be. So definitely you can join that.
Sure.
Yeah, and I think we'll try and organize this gathering through this Telegram group that I mentioned.
That'd be great.
So if you want to join that, do DM me on Telegram. I'm Justin Drake, all lowercase, all one word. Thank you again, Dmitry. We're running late on time. I want to introduce our next speaker, Venkat Guruswamy from the Guruswamy Sudan paper. Thank you so much for your patience, Venkat. We're running about 20 minutes late, but I've given a heads up to folks, and I expect many people to stay an extra 20 minutes. The floor is yours.
All right. Can people see my slides?
Yes.
Okay, great. Thanks again for the patience. I know the call has already gone for a while. I only joined midway. Yeah, I'll be talking about positive results which show proximity gaps hold, albeit for some variants of Reed-Solomon codes, namely something called folded Reed-Solomon codes, and also when the evaluation points are chosen at random. And this is joint work with Rohan Goyal, who is a PhD student at MIT. Okay, so very quickly, some background mostly to set notation. Code alphabet will be sigma, length n. Delta will be relative Hamming distance for us. And the distance is the usual thing, the minimum relative Hamming distance between pairs of distinct code words. And the rate is the usual stuff. Okay, so all this is standard. And we will be talking about linear and additive codes. So maybe the first thing to slightly point out is that we all know what linear codes are, which are just a linear subspace over the underlying field. An additive code is also a linear subspace, but the alphabet is it's like a vector code. So each symbol is a vector over the base field. Okay, so it could be a FQ linear code, but each symbol is FQ to the 10, let's say. Okay, and this comes up in these folded Reed-Solomon codes. Okay, so that's maybe one small change. So, but of course, our results on random Reed-Solomon apply to usual Reed-Solomon. So we also have things for linear codes, but additive codes come in. So what are proximity gaps? Obviously, this audience doesn't need this definition, but just to set up some notation, and I will only focus on lines. Our results in the paper are worked out for curves and so on. This basically says that if you have a line where there are sufficiently many points close to the code, then in fact, all points on the line are close to the code. Okay, and pictorially, so you have this line here where a few points are close, then all are close. And this delta is the proximity parameter, epsilon is the error. Hopefully, these are standard notations. Now, a code has delta epsilon correlated agreement if basically under the same premise, not only is the entire all the points on the line close to the code, but in fact, they are close to a line of code words. So namely, there's exactly what this red line thinks. So you take a C0 and C1 and take the line through them, and that entire line is actually close to this. Okay, so this is a more geometric picture. So you kind of know that the proximity arises for this geometric reason. Again, standard definition. Please stop me if something I'm saying is not clear, but so far, same thing, right? So it's just this is a stronger notion because this, of course, implies this, because every one of these points on this red line is a code word being a line of code words. Great. Reed-Solomon and friends, we all know what Reed-Solomon codes are. So you have an evaluation points, take degree k-1 polynomials evaluated at n points. The alpha i's are the evaluation points, usual stuff. Now, a standard Reed-Solomon code has arbitrary evaluation points, or maybe you pick it from some nice subgroup, so you can do some good algebraic FFT and things like that. For a random Reed-Solomon code, you simply take a field a little bit larger maybe, but then you just sample n random points from it. Okay, so you pick the evaluation points uniformly at random. And there is also folded Reed-Solomon codes, which are like Reed-Solomon codes, except you essentially bundle every consecutive. For example, if you order these things as alpha, alpha, gamma, and so on for some primitive element, you literally take every S symbols and bundle them together as one mega symbol, one vector. Okay, so the ith symbol looks like this. The exact definitions are not important because I won't get to the details here, but this is what a folded Reed-Solomon code is. It's essentially very close to a Reed-Solomon code. And why do we do this? For list decoding reasons we'll come to in a second. Okay, so what is known about proximity gaps for Reed-Solomon codes itself? So by these beautiful results of Ben Sassan and others from 20 and this year, we know that they have proximity gaps for proximity up to the Johnson radius. And the error parameter is going to be small as long as now with the new result Q is linear in N. And these are based on list decoding algorithms for Reed-Solomon codes, as we saw. Now, one predicament is that for general Reed-Solomon codes, we don't have better list decoding results, and therefore, it's been hard to push beyond this Johnson radius. And in fact, a couple of these recent results, Stewart and the same paper, show that if you want to make the error really tiny, then there is a reverse connection. You have to do list decoding for proximity gaps. So, okay, maybe for slightly higher errors, you can get away without list decoding, but somehow the feeling is you need to list decode, and we don't know how to list decode Reed-Solomon codes. And what is list decoding? So a code is said to be delta L list decodable if no matter what point you take in a ball of radius delta around it, you won't have more than L code words. Compared to usual decoding where you want to correct uniquely, you will say that if I have a code of distance delta in any ball of radius delta by 2, I of course have only unique code word. But as you stretch the ball bigger, you can get more code words, and that's list decoding. And another way to say it, slightly goofy way to say it, but you'll see why in a few slides, is that if you take any L+1 code words close to some center, some two must be equal. You can't have L+1 distinct code words. Okay, and so that's just the contrapositive of this. And it's easy to see that if you have a code of rate R, you cannot list decode beyond 1 minus R. Your list size must grow exponentially then, so it's not possible. And I should say that your goal here is to keep L kind of small. Otherwise, the problem is not interesting. But the surprising thing is that this is a very simple limit, but you can actually approach that limit. So the list decoding capacity is actually 1 minus R. You can actually correct all the way up to 1 minus R, which is twice what you can do with unique decoding, even with the best codes. So in some sense, from an error correction standpoint, list decoding is very beneficial because it allows you to correct 2x errors. Now, as I said before, list decoding beyond Johnson is not known for Reed-Solomon, but about other codes. And about 20 years ago, we showed that this folded variant of Reed-Solomon codes indeed allow you to achieve list decoding capacity. So a small twist allows you to go all the way to the list decoding capacity. And there have been a lot of follow-ups to this and improvements on the list size parameter, which is an important thing, as was mentioned in a previous talk. And culminating in this beautiful result of Chen and Zhang from last year, which says that these codes, and in a more general class of subspace-design codes, are actually list decodable up to capacity with an optimal list size. This 1 over epsilon, I said the list size should be small, and they said it's as small as it could be for these nice codes, okay, which is a very, very nice result. And a similar result was also earlier shown in a pair of works, and we just published this jointly in a journal this year, that this also holds for random Reed-Solomon codes and random linear codes. So at least we do know codes which are list decodable up to capacity with the best list size. It's just that they are not Reed-Solomon. Very good. Okay, all this is about list decoding, and this is about proximity gaps. And I guess our main result is that we can translate these capacity achieving list decoding results, all of the known ones so far, to proximity gaps. So essentially, basically all the codes we know decodable to capacity have proximity gaps up to this 1 minus R bound, with an error parameter like this, which another way you state is that the field size can be linear in N. And this holds for proximity gaps and correlated agreement, and also for mutual correlated agreement. Okay. And this class of codes includes, as I said, folded Reed-Solomon codes. The amount you fold needs to depend on how close you get to this 1 minus R bound. So that's the trade-off here. And it also for what are called multiplicity codes. Very simple. Instead of when you take a polynomial, instead of only giving its values, you give it the values of the polynomial and its derivatives at every point. This is perhaps more natural than folded Reed-Solomon even. So those also have this property. So your evaluation points can be nicely structured, but you just have to include the derivatives valuation as well. And this
we
also
have a question
holds...
from the chat here.
What
do you mean by
monitoring? Yeah.
Almost all codes here?
Yeah, maybe I should really say everything I know to be list decodable. Maybe I was just hedging a little bit, but all the positive results we know, I think at this point are translated. But I think it's important to point out we don't do it in a black box way. That's why I put this all. We basically take these results, and in each case we manage to get proximity gaps. But there could be some other result known which is not covered. Oh, actually, you know what? Actually, I take it back. There are these variants of algebraic geometric codes which are also list decodable up to capacity, and those we don't know how to get proximity gaps. So that's what almost qualifies. Okay, so another way to say it is that this list here is almost many of the codes which are list decodable up to capacity. So we can also do some random expander based codes. I won't focus on it here. And for this audience, perhaps most interesting is the random Reed-Solomon code. So if your field is large enough and the length is large enough, this holds. Just for plain old Reed-Solomon, but the evaluation points, I can't tell you what they are. If you sample them randomly, you are in luck. Okay. That's the result. So hopefully I want to at least get the result statement clear. So essentially we get proximity gaps up to the optimal bound for these classes of codes. Hopefully the result is clear. If not, good time to ask before I move on to some techniques.
Yeah, pretty clear.
Pretty clear, great. All right. So techniques, I guess the crucial notion here, which actually already was mentioned in Ulrich's talk also, is this concept of line decoding. And this very much smells like correlated or mutual correlated agreement, but we somehow ferret it out and we use that to do all our results, which made our life nicer. So what is informally a code is, a bunch of parameters here. A code is delta AB line decodable if the following picture happens. If you take any A code words, which are all close to some line, then among themselves, you have many, a smaller number, B will be smaller than A, which are themselves collinear. Okay, so that's somehow the idea. So if I take this red line here, and there are many code words which are close to it, then in fact there are many on a line. Actually, the red are so the red line is the code words line. And so if any A code words close to a line, at least B of them themselves will lie on a line. And there are extensions to curve decoding and so on. I'll define this formally in a second. And the nice way to think about it is that list decoding says there aren't too many close by code words to a single point. Line decoding says there aren't too many non-collinear code words close to a line. So it's some sort of a degree 1 version of list decoding. Okay, and this is also why I stated the previous thing like that. So here we are saying that if there are many code words close to a line, enough of them are collinear. Much like for list decoding, if there are many code words close to a point, some two must be identical, okay, which is like a degree 0 constraint. So this is the formal definition. A code C is delta AB list decodable if for any A points on a line which are close to some code words, those code words themselves, at least B of them lie on a line. Okay, so you take any A points, any code words close to A points on the line. Among them, there are B of them, which themselves are on some line through C and C. Okay, and this is somehow in various forms implicit in, I think, many works. And it's also the crucial notion driving our work. Okay, so with this, actually, our proximity gaps breaks down into very nice modular connections. So the first thing, and I have a slide on this, if I have time, I'll show it. It's very simple. If I get enough points on a line if I have delta AN line decodability, where N is the length of the code, then I immediately get correlated agreement. Okay. So essentially, to prove correlated agreement with A exceptions, I just need to find N points on a line amongst any A which are close to a line. Okay, this is good, but getting N points collinear may be difficult. And then we give a simple combinatorial reduction to say that actually it suffices to get 3 points on a line, which is the first non-trivial thing, right? Some degeneracy. And that we can amplify to getting any number of points in the line by giving up a little bit in the exception parameter. Okay, so this A becomes A square. And the final thing is that, and this is important for us to get really good error parameters, if we combine line decodability with normal list decodability, then we actually get correlated agreement. And the difference between these two is that now the error parameter is much better. Okay. And the nice thing is this is each of these is very simple combinatorial reductions. In fact, I think the union of all these proofs may be 2 pages in our paper. But with all this, all that we have to do is to get 3 points on a line, and then by these lemmas, you're done. Okay, so that's the goal. Okay, so now I'll talk a little bit about subspace. I'm not monitoring your chat, but if there are any questions, just feel free to unmute and ask also.
We do have people that are surprised that the result holds on for random Reed-Solomon codes.
Oh, okay, good.
Was it a surprise to you?
Yeah, I guess in some sense, yes. Yeah, I mean, it was also, you'll see in a bit, it was also a bit serendipitous that certain results came out, which translated results from subspace designs to random Reed-Solomon just a few weeks before, and as we were working on this. So it was good timing for us. So if I take the union with that result, then sure, it's surprising. But
got it.
Okay, I'll talk about subspace design codes because that's what we were actually working on in trying to extend some list decoding things. So these additive codes, as I said, each symbol is a vector. So each coordinate itself is high dimensional. Can we get more structure out of it? And this definition is a bit technical, but you don't need to understand it. But the point is an additive code is a subspace design if the following holds. If I take any low dimensional space of code words, things like lines or low dimensional subspace, then what happens is that if in that subspace, I look at those code words which are 0 on the ith coordinate, that's going to drop the dimension of the subspace, perhaps. And the subspace design says that that happens very nicely on the average. When I take a subspace and I set each coordinate to 0, the average dimension drops by a factor of almost the rate, which is the best it can drop. Okay, it may not be clear why this is the correct notion. I don't have, this talk, it's not long enough to convey that, but this is the key common notion property of folded Reed-Solomon codes. So Swastik, Kopati, and I showed that folded Reed-Solomon and multiplicity codes are subspace designs. And these recent line of works have brought to the fore that this subspace design property is really the core of a lot of list decoding results. And this nice paper of Brackenshek et al. Showed that these folded random linear codes are also subspace designs. So these arise in many places. And how are subspace designs used? Just a bit of a schematic. For list decoding, with Carol Wang, we showed for folded Reed-Solomon codes and also holds for subspace design codes is that if I take the proximal code words to a point, they must belong to a low-dimensional subspace. And then there has been a very nice line of work listed here, which showed that in a low-dimensional subspace, you cannot have too many code words. So essentially, it showed list decoding bounds for low-dimensional subspaces. And now for line decoding, we literally translate both these steps. So first, we show that the code words which are close to a given line as opposed to a point also lie in a low-dimensional space. And this pretty much follows from the definition of subspace designs. And then following the second step, we only then have to prove line decodability for low-dimensional subspaces because we know that all code words of interest to us are pinned down to a low-dimensional subspace. Okay, and that's how we prove things for subspace designs. But of course, people are surprised about the random Reed-Solomon result. How do we do that? Okay, so for that, there's been a beautiful line of work on what are called local properties. I won't define them formally, but essentially these are properties about small sets of code words. Like, for example, a small list lying in a small ball. And there has been a beautiful line of work trying to understand when local properties hold for random codes of various forms. And a remarkable result here by Levi Moshe Shagritaya, which appeared in Fox this year, just earlier this week, I guess, showed that all LCL properties of random linear codes also hold for random Reed-Solomon codes. So if you want to tame random Reed-Solomon, you just have to tame random linear, which sounds much easier because there is more randomness. And then this work of Brackenschik et al., and this was the serendipitous thing which I was mentioning, said that if I prove a local property for a subspace design code, like a fixed code, like or all subspace design codes, like folded Reed-Solomon codes, then they also hold for random linear codes. And then there's one more result on expander codes, which I'll skip. But just even putting the first two things together, we have this nice compiler essentially saying that if we can focus on local properties and we can prove it for subspace design codes, then we have it for random Reed-Solomon codes. And that's essentially how we made the connection to random Reed-Solomon. But of course, this requires casting this line decodability as a local property, which unfortunately does not seem easy or even true as is. But we make a variant of line decodability, which essentially line decoding is some sort of degeneracy, right? It says 3 points are on line. And we essentially replace that by something we call V decoding, which then fits into the local properties framework. And these are up to some small loss in parameters equivalent. So then we show V decoding for subspace design codes, as I indicated earlier, and then by these beautiful body of results, we have them for random Reed-Solomon as well. Okay, so some work goes into casting line decoding as an LCL property, but that's really what we do. Okay. So I'm almost out of time. So this is our result again. We get proximity gap all the way to capacity for folded Reed-Solomon and random Reed-Solomon. I've just stated the result again. I had a couple of slides on techniques, but I'm going to skip them. But I will just say that the way we prove line decoding leverages some very nice recent progress on list decoding algorithms and how you prune a subspace which contains the list to actually find the list. Okay, and this is the entire thing. And I should say that each of the steps we have is very simple and just pretty short. And I mentioned that line decoding implies correlated agreement. That was implicit in previous works. And if you want, the full proof is in this slide. Okay, so really, and there's not too much going on. And perhaps one novel part in our thing is that we take line decoding plus list decoding to improve the error in correlated agreement. And this is also not very hard. And this goes by allowing some proximity loss in an intermediate step and then leveraging the list decoding to improve parameters. And it's also pretty short. Okay, so these three are the ingredients. Okay, so that's, I think I'll close more or less on time. So folded and random Reed-Solomon codes are optimal proximity gaps over linear size fields. And this is enabled by this clean abstraction of line decoding, extending list decoding algorithms, which have been found to line decoding by suitable subspace pruning, and using these nice results to translate from subspace designs to random Reed-Solomon codes by carefully casting line decoding within the framework of these local properties. Okay, so I think I'll stop there.
Thank you, Venkat. What a great way to end. Any questions from the audience?
Yeah, I have a question, if I may.
Go ahead.
Yes, of course.
It's a bit of a technical question, but in the definition of the folded Reed-Solomon code, you have this like geometric progressions on which you evaluate.
Yes, yeah.
The gamma in the progression, it needs to be a generator still? Because
it doesn't have to be a generator. It has to have large order. Let me see.
Because I saw that like in the reference that you use, it is written that gamma is generator, but now you drop this condition. And so, because somehow you can't let the domain to be a subgroup of the multiplicative group, right? Or
so actually, yeah, you're absolutely right. The original work with Atri Rudra, where we proved these achieved capacity, that used a different proof, and there it was important that gamma was a generator because it required that certain polynomial was irreducible.
Okay.
But there was this later linear algebraic approach to decode, and that only required that gamma has large order. I believe the order just needs to be more than k.
Okay, so you need large order of gamma. Okay.
Large gamma has to have large order. Yeah.
Okay, fair enough.
So maybe a question for me, like we saw like we have random Reed-Solomon code achieving least decoding up to capacity with a probability, and also having mutual correlated agreement up to capacity with a probability. Is there anything known about the correlation like of these two probabilities? Like if I sample if I sample a random Reed-Solomon code, is it possible that I get one property, not the other, or am I? It would seem surprising.
That's a great question. Yeah, I think both of these follow the same framework. So the probability bounds you get will depend on like how local the parameter is and so on. I suspect that the property here is a bit more complicated. So at least the tail bounds we get may be weaker for proximity gaps. And it's important to note that we are not saying like list decoding implies proximity gaps. So you can certainly get both combinations. You can actually I don't know if you can get proximity gaps. You can probably even get proximity gaps and not list decoding, get list decoding and not proximity gaps. And of course, with high probability, you will have both because so.
And what's your intuition? Like you don't get a black box result here. You have to use the actual properties of the code, these subspace designs. Like, do you believe there's something more that we can be said about the black box relation of these two notions, or
yeah, at some points when we were working on it, we even thought with some exponential loss in this epsilon, right? Like, we might even get some black box notion, but those turned out to be misguided. So I'm not sure. I don't think it's ruled out, but at least currently, essentially you're decoding many code words and you have to correlate them in some way. And that seems hard if you only assume a black box list decoding statement. Right.
So. Maybe stronger thing like least recoverability could help, or do you think it's?
Yeah, actually, in a way, list recoverability played a crucial role in this genesis because essentially a line is in each point you're list recovering a set, but it has a low dimension thing. So list recovery did inspire some of these things. So you're right. I mean, in some sense, this line decoding was an abstraction of the kind of list recovery guarantee you would need to then get proximity gaps. So, but yeah, so it's black box around line decoding, but you could argue whether line decoding is essentially the same as MCA or not. So,
thank you.
Again, did you say that you have an explicit example of a code that's list decodable but proximity gaps are false?
No. I was just answering Giacomo's question that these are both probability results. So it's the sample. The success events could be each could happen and not the other. So.
But do you know an example that's list decodable but proximity gaps are false?
No, I don't. Yeah. So yeah, I was just saying it's possible that
Dan, I thought there was
that's not ruled out. No, neither event dominates the other is what I was saying.
Dan, I think there's the not for the random Reed-Solomon code, but there is that example in the Deep Fry paper, the 1.5 Johnson we looked at some time ago, I think.
Yes.
When you zoom out, the SNARG industry has basically gone all in, or essentially all in on Reed-Solomon codes. I'm wondering if you, as a coding theory expert that knows the whole zoo of codes, could basically help design new SNARGs as opposed to us trying to improve our understanding of Reed-Solomon codes. So I guess I'm wondering, like, do you think there's an opportunity to use folded Reed-Solomon codes or random Reed-Solomon codes to design new SNARGs, and is that something you're interested in?
Yeah, I definitely, one thing is, I don't know the full practical parameter space that well. But one thing, in a way, folded Reed-Solomon codes just compresses things. I mean, I assume you would want to keep the same proof size and query complexity, and those are very paramount, right? So a priori, I don't see why. I mean, I think attempting to use folded Reed-Solomon in some of these things seems at least worth a try. But I don't know enough of the design space to have a sense if, that is something, a no-go or maybe worth at least spending some time on. So.
Maybe I can comment a little bit on that because I've been thinking about this. The kind of annoying thing that happens when you use folder with Solomon code in some of the protocols I was looking at is that going from like Johnson bound to capacity is around a 2x saving queries, which you can also achieve by just increasing the rate by a factor of 2. And so when you run the numbers and you look at the proof size resulting from like the folded read Solomon code and usually it turns out that just using a bigger rate is somewhat better for like your argument system.
I see. But I guess then you can only check proximity to close. I mean, your proximity radius obviously will drop, right, as the rate increases, and that's okay.
Yeah, exactly. You're saying it's probably still all right because at the end, what I care about really is the number of queries, and if I do 128 or with rate 1/4, 128 with rate 1/2, the important thing you can always trade off prover time with you can always trade verify time with query complexity, and with Solomon codes the is good enough that actually is not that bad. But it might also be that I have miscalculated something. So this I'm also gonna double check again.
Ulrich is asking, what about the encoding cost for folded read Solomon codes?
Oh yeah, I guess it's same as encoding cost of read Solomon, right? Because you just encode it and bundle the points. And unlike random read Solomon, you can pick your evaluation points to have any nice FFT conducive structure as you would like. So encoding complexity is the same. Yeah.
And Venkat, in light of the recent attacks on the conjectures and the evolution of the conjectures, like, do you feel kind of bullish or bearish on kind of new insights that at least partially replicate the results on random read Solomon codes to non-random read Solomon codes?
Yeah, I think that's a great direction. I think, clearly we know these things exist in abundance. So finding an explicit evaluation point where you can beat Johnson is, a very fascinating question. And I think this has come up in various things as well. Maybe looking for special fields like prime fields and special evaluation points. Maybe there is something. The trouble is that we don't have a good pseudo-random criteria for what these evaluation points should be. So if we gave some crazy criteria saying that if these alpha I satisfy this, then you will have this property, then presumably you can, throw a lot of number theory at it or other things to try to find these in some prime fields. And we don't have that understanding yet. So perhaps inspecting these random read Solomon proofs to sort of see really what they're using may be a good direction.
Okay, well, I don't see any more questions, and we've been at it for 2.5 hours. Thank you so much to all the speakers. Thank you, Venkat, and thank you to all the attendees who made it this far. Have a great day. Bye, everyone.
Thanks. Bye.